Good morning slash afternoon slash whenever you're watching this. Happy Wednesday, I think it is. I think I said Monday in yesterday's video, so now I'm all sorts of mixed up. Anyway, happy day, whatever one it is. If you haven't yet watched the hummingbird video that's attached above this one on Classroom, don't watch this until you've seen that one. This is going to go directly off of that, so watch that video first. I thought it was pretty cool. If you haven't watched it, go do that now. I'm going to turn this light on so I don't look like a scary shadow. Ooh, it's bright. So watch that first before you watch this one. We're going to talk about it a little bit in what we go over here. So we are going to keep going with Punnett Squares, but we're going to tie it into, if you remember, right after we took the Earth Science test, it was 2, 3, 4 weeks ago, something like that. We watched Planet Earth, the Jungles episode. And in that episode, we saw a number of things. We saw capybara. We saw the caimans. I think there were jaguars as well. And we saw kind of how they all interact in the jungle environment. But we also saw hummingbirds, and we saw a particular kind of hummingbird called the swordbill, which is what we're going to base this activity on. So I linked this particular sheet that we're looking at here. Obviously, you can't type in it. I mean, you could try. It's going to be a little bit tricky. So I'm not going to ask that you fill this thing out and give it to me. What I want you to do is take a separate piece of paper. And then as I do the Punnett Squares in here, I want you to do them with me. So that way you can see if you're doing them correct. So in other words, when I start to do the Punnett Square, pause, you do it first. And then you can watch me do it and see if you're understanding it. And if not, shoot me an email. Let me know so I can help you out. But just get a scrap piece of paper. I don't need you to turn it into me or anything, just so you can do the Punnett Squares and kind of test yourself to see how you're doing. Okay, so we're going to talk about hummingbirds. I thought that video was pretty cool. Hopefully you did too. If you guys have a hummingbird feeder, either at your house or at a park nearby, if you watch hummingbirds, they're actually kind of jerks. They're not very nice to each other. Like that video shows, even in our backyard, we have a feeder. And you can make your own stuff to put in it. It's just sugar water. You have to get like the ratio right or whatever, but you can make your own feed for them. And we get a lot of hummingbirds out here, but they do fight each other. If there's more than one trying to get onto the feeder at the same time, they'll fight just like in that video. And they have the really pretty colors like the ones in the video do too. Obviously not the same. Those are from Costa Rica, but hummingbirds in general are just really, really cool. So we're going to use them to talk about Punnett Squares. So talking about tracking traits across generations. If you remember, a Punnett Square helps us determine the probability of a trait showing up in the future. I'm just reading that top line there. In future generations and across between two parents. Remember, Punnett Squares, they're not telling you that you're having 4 offspring. They're telling you what are the odds that one of your offspring are going to look or have a certain genotype, look a certain way or have a certain genotype. So Punnett Square not having 4 offspring, instead figuring out a ratio or a probability, 1 in how many chance that I'm going to get this particular trait or this particular offspring. Remember, you can write it as a fraction. You can write it as a ratio. I don't think I told you that in yesterday's video. You can write it 1 to 4. You can write it 1/4, or you can write it 25%. Either way, I tend to go with the fractions and then the percents personally, but you can do it either way. Okay, so in hummingbirds, I'm reading the second paragraph here. In hummingbirds, the allele for short beak S, sorry, that's big S, is dominant. So short beak is dominant, and then we've got the allele for large beak is recessive, the little s there. If 2 hummingbird parents with genotypes big S, and small s were crossed, what are the possible outcomes for their offspring? Okay, now here's an opportunity where you're probably going to want to pause, see if you can set this Punnett Square up correctly, and then hit play, and I'll do it. So I'll give you a second to do that. Sorry, got a little bit of an itch. Oh, I threw my pencil. Hate it when that happens. All right, so I'm going to set this Punnett Square up. Parent 1 is going to go up top, and parent 1 is right here. We've got big S, and we've got big S. And then parent 2 is right there, and they're going to go on the side. Ooh, that's a little too big. I'm really bad when it comes to S's. Drawing one that's clearly dominant and clearly recessive. That's a little bit better. Okay, now remember the top ones here are going to work down like this. So we're going to take those two big S's and we're going to drop them down. Big S there, big S there, big S, and big S. And then remember, these guys over here are going to work to the right. They're going to go that way. So small s in, small s, small. There we go. Okay, now you might notice right away, these offspring aren't really diverse. Like you've got, look at what our genotypes are here, and we'll list those down below. We've got big S, small s for all four of them. So genotype possibilities are kind of lame. You can only get one possible outcome with these two parents, and that would be big S, small s. Now, phenotype-wise, what does that mean? Well, let's go back and see. Our dominant trait is short beak right there. So all of them have a single dominant trait in them, which means they're all going to have that phenotype, which is short beak. Okay. So we got a whole bunch of short beak offspring. No matter how many times these parents breed together, all we're going to get is short beak hummingbirds. Sorry, I blanked on what we were talking about. So this guy right here would be our short beak. And so these two parents, they're not going to have any genetic diversity when it comes to beak size. All their offspring are going to be identical in terms of their beak trait. Okay. So that doesn't mean that they're going to have identical offspring. That just means no matter how many times they breed, they're always going to get the same phenotype, genotype for this particular trait, for this allele combination. Let me get rid of all this. Quick note, this is generation 2. That's going to come in handy in a second. Let me see if I can actually just kind of leave it. No, it won't let me scroll, will it? Okay. Let me get rid of all this fun writing. There should really just be a clear button, but that would be too fancy. Okay, let's go back to pencil, or back to mouse rather. Oh, I bet I could have just scrolled like that. Oh, well. Okay. Here we go. So first question says, compare and contrast the resulting offspring to their parents' genotypes and phenotypes. How are they similar? How are they different? So what we're going to say here, and I don't want to type, or I don't want to handwrite that. That's going to be pretty rough. So I'm going to type this. So let's think about their parents. So parent 1 was big S, big S. Parent 2 was small s, small s. Oop, not 3 of them. All offspring would be big S, small s. So in terms of comparing the genotypes, the offspring are all going to be different from the parents, right? There's no offspring that are going to be big S, big S. There's no offspring that are going to be small s, small s. All offspring would be big S, small s. So that's one difference in terms of genotype. Now, phenotype-wise, let's see. All of the offspring would have what kind of beak? Short beaks. Parent 1 was short beak. Parent 2 was long beak. So we've got kind of some similarities, kind of some differences. So all of the offspring are going to have different genotypes from the parents. Nobody's going to get a big S, big S. Nobody's going to get small s, small s. But the offspring would be phenotypically similar to parent number 1 because they're all going to be short beak, and parent 1 was short beak as well. Nobody is going to be similar to parent 2 in terms of beak size because parent 2 is long beak. Okay. So let's continue from there. It says take offspring number 4 from generation 2 above. You remember everybody was big S, small s. I've got some old drawings laying around up here. Here we go. So offspring number 4 would have been big S, small s. And then let's go ahead and see what it wants us to do here. So take offspring 4 from generation above. Offspring 4 reaches maturity and crosses with a new hummingbird with the genotype big S, big S. Let's show all possible outcomes. So offspring number 4 from above big S. Let me retry that. Not a huge fan of that. Big S, small s. Slightly better. It reaches maturity and it's going to breed with one that is big S, big S. Okay. Now, again, if you want to do the Punnett Square right now, this would be a good time to pause and then you can play and I'll show you whether or not you did it correctly. So top ones are going to come down. We got a big S here, small s, small s. Excuse me. And then the left ones are going to come to the right. So big S, big S, big, and big. Now you're going to notice right away, we've got a little bit more diversity when it comes to beak size traits. Phenotype wise, it looks like we're going to be pretty disappointed again. There's no diversity, but let's get our genotype. So I could be big S, or I could be big S, small s. Okay, so we can have two different genotypes in this third generation. And then phenotype wise, we're going to have all, I'm just going to write small beak. And that's it. Okay, 100% of them are all going to be small beak. If you're asking why, how do we know that? Because everybody's got the dominant trait still. Remember, the dominant trait is going to be small beak. Everybody's got at least one of those. Okay, so let's go down. It would be pretty groovy. Can I? Oh, I can leave it. Look at that. Sweet. Okay, it says, how is generation 3 different from generation 2? So if we remember, in generation 2, everybody was big S, small s. Okay, do we have a difference now? Well, yes, we do. We've got some that are big S, and some that are big S, small s. So we're going to say here, generation 3 has, let's say, 50% chance of, let me say genotype, big S. Whereas generation 2, I am struggling with my typing today, had a 0% chance of big S. Okay. So in other words, the main difference between generation 3 and 2 is now you could potentially have two dominant traits. If you are either this one here, oh, I didn't switch back to pen here. If you're this one or this one, so there's a 50% chance that you could have double dominant traits in generation 3. And in generation 2, there was no percent chance that you could have that. None of has there. I hate when the spell check thing has things underlined. It always bothers me. So that's our main difference. If it was, I guess we should probably compare the phenotype as well. It says, how is generation 3 different from generation 2? But that would be a similarity. So there, we don't have to worry about that. So everybody's going to be small beak again in this generation, just like the last one. So we don't have to worry about that. Now it says number 3 here. Is it possible for any of the generation 3 offspring to reproduce and have a large beak offspring? Why or why not? So let me clear this out. Okay, so we're talking about these guys right here, generation 3 offspring. Could they potentially breed with another hummingbird and produce a large beak offspring? Okay, this is a tough question. I want you to ask or answer this right now before you go on. Take a lot of time on this. Think about it. Is it possible for any of the generation 3 offspring to reproduce with any hummingbird out there that has any alleles for beak size and create a large beak offspring? So think about it. Answer on your scrap paper. I'm going to sit here while you pause, and then I'll start kind of going over it with you. Okay, you answered it. Great. So the answer here is yes. Now we need to explain why that is. Okay, the only way this is possible. So I'm going to say the only way a generation 3 hummingbird could produce a large beak offspring is if a big S, small s crossed with either a big S, small s, or small s hummingbird. Okay, so what does that mean? Maybe that answer doesn't seem terribly clear to you. Let me clear this real quick, and then I will explain. I wonder if I can do now. There used to be a fancy smartboard trick. If you guys remember smartboards, does anybody at school still have a smartboard? I don't think I've seen one in a long time. But anyway, if you wanted to erase something, you could just draw a circle around it and then click, and it would all go away. That would be pretty handy right now. Okay, so let me go up just a little bit. I'm just going to use this Punnett Square for an example. Don't worry about this. So the question is, could any of those generation 3 birds reproduce to make a small beak hummingbird? Sorry, offspring. So the only way that's possible is if it was a big S, small s from generation 3. Remember, there's a 50% chance in generation 3 that you could be big S, small s, and there was a 50% chance that you could be big S, big S. Okay. Now, the reason that we know it has to be big S, small s is because check this out. If I were to instead take one of the birds that were 2 big S's, okay, those top ones work down, right? So we would go here and here. Immediately, all 4 of our squares has a dominant trait in it. So there's no way, it doesn't matter what the other parent would be, because it's all just going to be overshadowed by those dominant traits, okay? So when it comes to getting the recessive trait, you got to have at least 1 per parent if you want any of the offspring to have it, okay? You can't have a homozygous dominant parent, or else all of the offspring are guaranteed to get 1 dominant trait, and then they're not going to be able to have the recessive phenotype. So let's go back to big S, small s. And then if this bird was to breed with a big S, just like I said, it's over. Okay, so this bird would have to breed with either a big S, small s, or a small s, small s. And let's do the Punnett square real quick. So let me fill this in. Small, small, big, big, small, and small. Okay, so in this case, you've got half of them, 50% chance of being dominant. Oh, I'm sorry, this one as well. So 3 out of 4 chance. And then you've got this 1 out of 4 chance here of having this the long beak, the recessive trait there. Okay, so if you breed a big S, small s, and a big S, small s, you're going to get 3 out of 4 of them, 75% chance that you're going to get the dominant trait, but there's also a 25% chance that you'll get the recessive trait, which is that 4th box that I just erased. Okay, now let's keep the same bird from generation 3. Sorry, this eraser's very laggy. And then let's say instead of breeding with a big S, small s, I'm just going to start over here. So generation 3 bird was big S, small s. And then let's say they breed with a small s, small s. So I've got big here, small, 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 and small, small. Okay, so if I take a big S, small s, I cross it with a small s, check this out. Now I've got a 50% chance that I'm going to get a long beak offspring, okay? I still have a 50% chance that I'm going to get short beak. There's 2 out of the 4 that have the dominant trait in there. But the question was just asking, is it possible for any of the generation 3 offspring to reproduce and have a large beak offspring? The answer is yes. And the only way it's possible is if it's big S, small s, and they breed with either a big S, small s, or a small s, small s. I have so many smalls and s's and bigs and s's. Okay. Hopefully that makes sense. This is kind of the trickier thing with Punnett squares is how can I predict how is it possible to get a recessive trait passed on, right? Or how is it possible for a recessive trait to show up in the next generation? So this is going to lead us into a new discussion here. You may have heard of the expression like a certain trait skips a generation. And it could be anything. It could be eye color. It could be height. Some people always say they say that particular trait, oh, it skips a generation. So here's how that's possible now. You can see, depending on what traits your partner has when you're breeding, you can have something show up or you can have it not show up, okay? And even if you both have the smallest trait, both of these hummingbirds have the smallest trait, there's still a chance that they could have 10 offspring and none of them get the smallest, right? I mean, it's a simple game of odds, right? Sure, there's a 50% chance, but if I'm flipping a coin, I can get 7 heads in a row, right? Just like male versus female, when you're having a baby, it's still a 50% chance, but some people have all boys, some people have all girls. It's a flip of the coin. So it's possible that even though you have that recessive trait and your partner has that recessive trait, you'll never have an offspring that is recessive. It's also possible that you could always have recessive offspring, right? I mean, the coin can flip either way. So maybe these two hummingbirds, the one short beak, the one long beak, maybe they have all long beak offspring. Okay. It's just a flip of the coin. And sometimes that's the way it goes. Now we got one more question here that we're going to look at. So this paragraph right here is where I'm going to be reading. If I asked you to continue crossing generation 3 to form generation 4, 5, and 6 and create a Punnett square to show the offspring probability of each generation, you could easily see how tedious and time-consuming that would be. The question becomes, is there a better way of tracking traits across numerous generations? So think about this. If I said, hey, can you tell me what are the odds that generation 6 is going to have a long beak in it? Can you imagine sitting there and going, okay, generation 4, Punnett square, generation 5, Punnett square, generation 6, Punnett square. It's going to go on and on and on, and that would be awful. So I want you to try to brainstorm, come up with your own system here, okay? And this is your assignment. I want you to submit what you've come up with to me, whether you want to take a picture of it, whether you want to share this document with me. An easy way would just be screenshot on your Chromebook, whatever you come up with, or if you're writing it on paper, take a picture of it and email it to me. I do want you to turn this into me, though, because I want to see what you come up with. So give me a better system than just doing Punnett square after Punnett square for tracking beak sizes of 3 generations of hummingbirds. Now, if you look right here, I want you to include, oh, I'm not on my pencil again, sorry. There we go. I want you to include gender of the bird, whether they have large beak or small beak. So 3 generations worth of offspring production, okay? I want you to come up with a way of visualizing this that's not just 3 different Punnett squares, okay? The point of this is not do a bunch of Punnett squares. I want you to come up with a better way of showing gender of the birds and then beak sizes over the course of 3 generations, okay? You can get creative, okay? You can make all the birds female, all the birds male. You can make it a mix. It doesn't matter. I just want to see what kind of system you come up with for visualizing this, okay? So that's your assignment for today. When you've got it done, whether you do it on the computer, whether you do it on paper, take a picture of it, email it to me. I think that would be the best way. Yeah, because I can't, Classroom won't let me put a spot for you. Well, maybe it will. I'll look into it, but for now, email it to me. And then when I do the classroom post here, I'll let you know if there's an easier way to do it. All right. Hopefully this was helpful. As always, shoot me an email if anything's confusing. I know it's tough to do this stuff away. I wish I could stand there with you and help you out, but this is how we got to do it. So you got to reach out to me. I have no idea if you understand this or not. It's 100% up to you to let me know if you need extra help. I'd love to help out. Just ask. I'll talk to you guys later. Have a great rest of your day. Submit what you come up with to me. I'll see you later.